of bad statistics that superficially looks really good. This is, these 13 states need to lock down according to Harvard coronavirus experts. Well, the problem with any expert is I could go and find some other experts which will totally contradict the first group of experts, because experts are not that expert. It's just a label that you put on someone. You could say I was a statistics expert because I've got a master's. I wouldn't, but you could. And I could write all sorts of garbage and they could say, statistical experts say. So let's see what these guys say. Here's a map of the states, and they get a nice little coloured grid on the number of cases. So they've colour-coded it, which is fine. And they've colour-coded it in a very asymmetric way. Have you noticed that each colour code is not an even number? It changes. The first one has 0 to 351. Then it goes 473, 900, and it keeps on going up in weird. That I could live with. Here's the biggest problem. Dark is bad, lots of corona cases. Light is good, very few corona cases. So you look at this map, you would say Texas, Florida, and California are in real trouble. And I don't know what state that is, but whatever that is, Idaho, whatever it is got nobody in it, and that's a really safe state.
Wyoming.
Well, oh, you can tell just by looking. Right.
I just went there just a while ago, so,
right.
So I know.
Okay, so that's Wyoming. So you might think, well, what's the problem here? This data is totally useless. Telling me the raw data is not a good idea if you want to tell me about how many COVID cases are. Is there about 60 million Californians? Right? And I don't know how many people in that state. Shouldn't you be telling me the number of cases per 100,000 people? If a state's got 5 million people in it, couldn't it have 5,000 COVID cases? If a state's only got 500,000 people in it and it's got 5,000 COVID cases, in this map, wouldn't they be the same colour? Because they both have 5,000 COVID cases. But isn't 5,000 out of 500,000 totally different than 5,000 out of 5 million, or 50 million for that matter? That map is, it makes me wonder why that guy can even call himself an expert. Because that data is totally bad. You want to do a true comparison, you really have to do a unit comparison. How many cases per 100,000? Because then that factors in the size of a state, right?
So they say that Wyoming, that there's 578,000 people, according to 2019, that live there.
Right, so 500,000. How many live in California?
Sorry.
Millions, right? In this map, aren't they comparing them as if each state had exactly the same number of people in it? Because they're only telling you how many COVID cases there were.
Yeah, for California, it's like 39.51 million.
Right. So wouldn't California have 78 times more COVID cases just because it's 78 times more people?
Mm-hmm.
But this map doesn't tell you that, does it? No. Let's be silly. Suppose there's two towns, or a city and a town. Town A has 500 people in it, and every single one of them's got COVID. City has 5 million people in it, and 500 people have got COVID. If they did this map, wouldn't both those places have the same colour? Because they both have 500. That's not the reality of the situation. This is a just kind of thing that drives me crazy. Now, I can't understand why the person did that, because it's not something that's subtle and people would say, well, I never thought of doing it that way. I mean, this is blatantly bad. Any first year stats student would know that that was bad. Yet here it's been published like it's really important, and it's got an expert from some bloody place called Harvard In my opinion, Harvard has took a notch down on prestige if Harvard professors think that's good data. I'd be annoyed at it. If I knew what his address was, I'd send him an email, but they probably have laws against the email I would send him, so I better not. If you go hunting through the internet, you will discover, if you really look carefully, an awful lot of bad data. Right? People showing you things. Now, I can't think of any motivation because I don't think there is. I mean, California's very Democrat, right? And Texas is very Republican. So it's not like they're trying to show, you know, Democrat places have more COVID than Republican places. I don't see any, I don't know why he did it, except maybe, oh, okay.
Yeah,
maybe
the population, maybe.
Yeah, well, no, maybe it's this. He wants us to lock down 13 states.
Yeah.
So maybe that's, I don't know why he wants to do that, but that's why he wants to do it. It's
so California could technically, I mean, I don't know what it's like now. I haven't been keeping up, but could it technically be white then? If
I know it's not, but it could have been, right? Can you imagine that?
Yeah.
Imagine
if there
California.
were actually correct units, like
yeah.
Yeah.
I mean, if you're testing something, you don't need to know how many people have got the disease. That doesn't tell you what you need to know. Don't you need to know how many people per 100,000 of that population have it? Because doesn't that give you a better idea of how bad the infestation is?
Yeah, sometimes I hear statistics like 15% of people say this, or did this, but I wonder, like, out of how many people?
Well, that's true. I mean, that's one of the things you should give this, Gus. 15% of 100 is a very poor sample size, right? They asked 100 people and 15 of them don't like Pepsi or something, right? 15% out of a sample of 100,000 is really good data, you know? So if I see 15%, I don't really know whether I should trust that information or think, yeah, you only asked 100 people, it could easily have been 40%, right? It could easily have been 5%. When you ask a small sample, can you get an awful lot of variation? So if you don't tell me how big the sample is, I'm not going to put a lot of weight to whatever it says. If you can tell me, in fact, the best data would be, we did this, it was a simple random sample, there was 2,000 people in it, and the margin of error was plus or minus 1%. Now you give me that, then I'm good to go. Now I might not like what they tell me, but I will believe it, because that's what you're meant to do, right? You're not meant to say, well, I don't like that answer because it doesn't agree with my worldview. That's not how it works. Anyway, I got that little gripe over, because if it didn't, it would just bug me for the rest of the day, and I'd be even more distracted than I usually am. But if you, just as a little exercise if you want to, if you come across anything like that that's clearly bad, maybe we could share it and we'll have a look at it and see what's bad about it. I'm going to, I've been asked to do some questions from 7.3. So maybe that's where we should start first, and then we'll finish off 7.4, because we still have to do estimate of differences between two proportions, right? That's the bit we haven't done yet. And that's us finished as far as what we need for this week's homework. So it's good to know that we're actually well on schedule. One full week to go, and one more day, and then it's the finals. So, can I go? What's to come? We have chapter 8, which is to do with hypothesis testing, which is a bit like some lawyers got together and decided to interfere with the way statisticians work. So you'll have, it's a very precise way of proving something is true or not. It's called hypothesis testing. And then on Monday, we'll be doing 2 sections from what's called regression. And that's not too bad. Hypothesis testing will challenge you a little bit, I think, but I don't think the regression will, the last thing, which we'll do on Monday. So I'm back to 7.3. I'm loading up the questions as we speak. And, oops, it's not moving. My little thing's not moving. Right, it is now. So has anybody got a particular question that they were thinking about from 7.3? Right, what are you looking at right now? Are you looking at 7.3 or 7.4? Are you looking at any of those two?
7.3.
Oh, good. Okay. What was, whoever it was that asked, if you, maybe you can only do it by text, but hopefully you can tell me. Was it just in general, or do you want to see a particular question? Okay, I'm going to have to go out and in because that's the only way I can read chat.
One second, I'm looking. I don't think it was 7.3. It was.
So were you the one that asked for 7.3?
Yeah.
Okay, that's fine. I don't mind. Is it 7.2 or 7.4?
I'm going out and I'm gonna double check again.
Okay, we'll wait for a few.
While you're
yeah.
on 7.3, I actually
Do you have
did
a question?
have a question. Yes.
Okay, which one?
It's more on a concept, but it
Go for it.
appears on number 13 and 14.
Oh, quite near the end.
Yeah, and I don't think we covered finding n for a margin of error with proportions.
Oh, then you need to find out how to do that.
I peeked at the textbook, but it might be helpful to cover that.
I agree. I'm writing down the formula right now. Okay, so well, let's look at how big do you need to have a sample in order to get a particular margin of error, right? So that's what the question's about. So this is the formula that does it. So let's suppose I would like to know what n needs to be, right? And I want to get a margin of error of plus or minus 2%, so it's going to be 0.02. And it depends on what confidence level. So this number changes. If you want a 90, it's different if you want a 99. So let's just say, for argument's sake, that we did a 90. I hope it's getting to the point that most of you know the answer. What is 90, the magic number?
$1.64.
You are so close. One more digit and you got it.
Oh, 5 too.
Then you got it. Okay. Now, this formula has a weird guy called p hat, or if you want, you can call it P. And it's kind of back to front here. You're trying to find out what sample their size should be. So that technically means you haven't even done the thing yet, right? You haven't asked 200 people or 400 because you don't know yet how many people to ask. So p hat, there are two versions of p hat. If you know nothing, you have no idea what p is, right? It could be 0.1, it could be 0.82, you have no idea. When that happens, you choose the worst case scenario. The worst case scenario is p equals 0.5. So this formula will become 0.5 times 1 minus 0.5. The magic number is 1.645. The margin of error is 0.02 squared. So do you see we just basically plug in p hat is 0.5, the magic z-score, the margin of error, and you square it. And then you get your calculator to do the rest. So 0.5 times 0.5 times brackets 1.645 645 divided by 0.02, close the brackets and square it. Have we got a cat that wants to join in? Right. Do you notice that this number is a decimal, which is not a surprise, but we don't ask, we can't ask 0.2 of a person, right? So what do you think the rule's going to be in the rounding off? Is it going to be to the nearest number, or should we always round up?
Don't you round up always?
Correct. So if you knew nothing about a sample, right? If you didn't know whether it was going to be 22% people are vegetarians or 2% or whatever it is, you choose 0.5. That's just the rule, right? It's a worst case scenario. What that does is it guarantees that this will work. In fact, not only will it guarantee that you'll get that, you can pretty much guarantee you're going to get better than that. That's why it's the worst case scenario. Sometimes, hard to believe, but can we pretend that somehow you know it was 0.6? Now, maybe you've been doing this kind of survey lots of times before, and this is just another shot at it, right? Another example of you doing it. And all the other times it was about 0.6, right? Every time you got it, 0.55, 0.6. If you know the number, do you know the only thing you do here is you make this guy 0.6 and this guy 0.4, and you redo the calculation. So if you are told in the story that P or P hat, depends on how they want to phrase it, is going to be 0.6, then you change the formula to 0.6, 1 minus 0.6, which is 0.4, times this stuff. So here goes. It's going to be 0.6 times 0.4 times a bracket 1.645 divided by the margin of error, close the brackets, square the whole thing. Do you know, I can tell you right now, this is going to be smaller. That is always, when you use 0.5, that's always going to be bigger than you need to be. It's big enough to be safe, right? No matter what happens, it's going to work. Let's see what happens. Do you see it's now 1624? In the big scheme of things, would you agree it's not that many more people, especially when you need 1600 plus? Me being lazy, I would do it for this calculation, and then I'd probably go out and ask 1700 people, because it just seems, yeah, round numbers just seem better, right? You know, if you're doing something. Yeah, I'm not going to ask 482 people. Won't I probably ask 500? Yeah, it seems reasonable to do nicer numbers. So, are we cool with that, guy? It's just another formula you're going to have to write down and remember that this is the formula that you use when you're dealing with proportions. You know, so 20% of people are vegetarian, right? Those kind of stories, this is the formula, right? We did have a different formula, didn't we, when it was how big a sample needs to be if you want to get a margin of error of plus or minus 2 pounds, and it was a mean, right, an X-bar story. Remember that one? Right, in that version there wasn't like 2 situations, wasn't it? It's the same formula for every situation. Right, did you come up with anything on the questions?
Yeah, any problem from 7.2?
Oh, it's a 7.2. Okay, give me a few minutes to.
They're all the same problem, so it doesn't matter which one you do.
Okay, that's fine. I'm going to have to do some extra little things first. Estimating mean when sigma is unknown. Gotcha. Okay, so. And I should be able to go out and in, and we should see it. Are you looking at 7.2? Is it on the screen?
Yep, that's perfect.
Okay, so basically you do not know sigma, right? That's, You're still trying to estimate what the mean of a population is when you do not know sigma, the population standard deviation. That is typically the more realistic situation. And you can do it in two versions. There's the version where you're just given a whole set of data, which is this guy, and you're going to find the lower and upper limit of your 90, 95, 99. In this case, it would be a 90% confidence interval. And you're also going to be asked to calculate the mean and the standard deviation, but it's the mean and standard deviation of this data. Right? So this question is similar, this question is similar. Quite a lot of these guys. I'll do 5. Does that seem as good a question as any? As a representation? Okay, so I'm going to, you're just going to have to trust me. I'm going to leave this and go into the white screen to show you what the working would look like. So, clear this guy out the way. In this particular story, over the past several months, an adult patient has been treated. Oh, I remember this one, the calcium level one. Stage 1, get the data in. So you press edit. I'm just going to clear out this old data so that we're starting with a nice clean screen. There we go. And you type in the numbers and it's 9.5, 9, 10.5, 8.9, 9.4, keep going, 9.8, 10, 9.9, 11.2, and 12.1. So you collected a whole set of data, and now we're going to do an estimate of what the mean, right, of that population would be. That's a little sample from it, but what would the typical population mean be? These are pretty much all calculator orientated, right? There isn't a formula that you would have done for the 7-1, for instance. Right, you hit enter, and we go over to here, and now we have to figure out which guy in this very, have you noticed that this particular menu is quite congested? We use a lot of different things from it. So we have to know which one we're looking for. Well, we are looking for a t interval, right? Whenever sigma is unknown, you look for a t interval. If sigma is known, you do a z interval. It's a single t interval because this is a single sample. If it was 2 samples being compared, it would be the double t thingy, right? But this is a single one. So when I hit t interval, do you see I now have choices between statistics? That would be a question where they told you X bar was this, the standard deviation was that, and there were 200 people. This question, it's data that they gave me, so I'm hitting data. It's NL1, I'll hit that. Leave that as 1. In this question here, the confidence interval is a 99.9. Where did that come from? 0.999, okay. I never amazed. I think tell me if I'm wrong, did he do a 70, I'm calling him a he, could be a she. But did this person, did they do a 75% once? I mean, I have to take the space bar. Did this guy do a 75% confidence interval once?
Yeah, they did.
He did. That's, oh, he is not getting a Christmas card from me. Okay, 99.9 I can live with, because actually that is acceptable. It's extremely rare. Can you imagine how confident you have to be now? 99.9% confidence is kind of, you can take this to the bank. You know, you could almost bet your house on it. So here goes. And so we are going to come up with somewhere between, I'm calling it 8.5 and all the way up to 11.5. Okay, I changed my mind. 8.52 and 11.54. And that is the answer to the lower limit and upper limit. And then for free, do you see you get X bar is 10.03, that's in the question. And the standard deviation is 0.997 and some stuff, and that is in the question. So I'm now going to show you that my data did match, did match the calculations that we did. Can you see the 10.3 and the 99.7 and, oh, there we are, and the lower and the upper case. So it worked perfectly, didn't it? The calculator came up with the results. And then we'll do one of these ABCD things. Based on the results from B, do you think the patient still has a calcium deficiency? Well, if the average amount of calcium that this person has is between 8 and 11, I don't think he's got a problem anymore. A calcium deficiency was described over here as having a limit, having a level that's lower, 6 or lower. And when I look at this interval, would you agree that all these numbers are better than that? So he's totally fine now. So what would the analogy be in medical terms? Do you know vitamin D is sometimes prescribed because if you're not getting enough sun, you get these vitamin D pills and you take them and they up your vitamin D level. So it's a bit like that. You're taking a vitamin and it's, in this particular one, it looks like if you don't have enough calcium, you start getting muscle spasms. And all the nursing people here knew that, right? Or should know it, I'm guessing. And I remember last time I said, doesn't low potassium do something similar to you? At least I was told by my wife that if I get Charlie horses, that taking a banana helps. Are these wives' tales? Is low potassium, so there is a medical, knowledge behind that statement. It's not just a wives' tale. God, I've just been sexist and not even knew it. That phrase is called an old wives' tale, isn't it? That's a kind of derogatory term nowadays, isn't it? To heck with it. I don't mean anything bad by it, right? I would be quite equally willing to call it an old guy's tale if that's what the thing was, right? It wouldn't matter to me. Okay, so is that what you were looking for? The process of how you take data and use the calculator with T interval?
Yep, that's amazing. Thank you.
Okay, you are cool. So we're now going to look at our last guy in town as far as this section's concerned. So we must have shot through the other ones faster than I thought we were going to, but that's not a bad thing.
Can I check something quick just about the p-hat finding n for proportions?
Sure.
I just wanted to ask, so is 0.5 a good number for p-hat just because it's not too big or not too small?
It's actually, it's even more interesting than that. Do you know if you pick any number for p-hat that you like, right? So try 0.1, 0.2, 0.3, all the way up to 0.9. The combination of these two that gives you the biggest answer happens at 0.5. So when you pick...
I was like, I wonder if like 0.99 would be the worst.
Oh, well, let's show you. The rest of the calculation's the same, so we only need to work on this, right? So I'll try a 0.9 times a 0.1, right? That gets you 0.09, right?
Yeah.
A 0.99 times a 0.01, because that would be the other half of the coin, right? Now 0.99 is really big, but isn't 0.01 really small?
Yeah.
A 0.5 times a 0.5, you see how big that number is? That's going to guarantee, no matter what the real answer is, it's never going to be any worse than that combination of 0.25. So that's why if you don't know anything, you choose 0.5. And if they tell you a p-hat, then use it.
Okay, so the combination of 0.5 times 0.5 gives you the highest
Biggest, yeah,
proportion.
exactly.
Wow, okay.
I mean,
Thanks for showing me that.
it comes, if you want it, yeah. Oops. That's p, 1 minus p, right? I'm just using x's. That's x, take away x squared. If you sketch x minus x squared, when x is 0, you get 1. When x is 1, do you see right at the middle? At half, you get the biggest answer. That's visually why it works. So when you were picking 0.99, can you see why the answer was so low? Right. If you pick a number really close, like say 0.4, that's my last one. If you do 0.4, the other guy's 0.6, you see you get pretty good, but you don't get quite 0.25, right? You get 0.24. Can you see them kind of merging in towards the middle? So that's why 0.5 is used. Okay, so our last guy in town. How to estimate the difference in two proportions. This guy doesn't, or at least I won't show you the do it by hand version. They are notoriously ugly and really big. The analogy, do you know, I think I might have mentioned to you, I may even have shown you how to do the standard deviation by hand. Wasn't it horrendously messy and big? And we'll let the calculator do it. The mean isn't too bad. You could do the mean by hand, right? If I gave you 5 numbers, it wouldn't be a big deal. But if I give you 5 numbers and said do the standard deviation, it'd take you a fair chunk of time. So are we willing just to accept that it's just easier to use the features that the calculator has got for doing these questions? So what does the story look like? There are going to be 2 different populations, right? Let's suppose that we have one population is going to be Americans and the other population is going to be Scottish people. And we are interested in not what this guy is and not what this guy is, but what the difference between them is, right? The difference in their percentages, right? The difference in their proportion. And so we went and asked 1,000 Americans, so I'm going to call it N1, and we asked them, do you drink regularly? And then the small print is regularly means at least 3 times a week, right? So you have a definition. So do you drink at least 3 times a week? And these are adults. And these guys, 251 of them said yes. You know, proportion questions have to be a yes, no, right? So that's the number that said yes. Now, we asked, no particular reason, 500 Scottish people the same question. And out of that 500, 300 said that they drank regularly. So far, so good. Now, superficially, does it look like Scottish people drink more than American adults? Which is what my story was meant to do. But is that really true? What we're going to do is we're going to look at the difference. Right. Now, forget about this story just for a minute. Imagine I have a difference and it says -5% to -1%. And I have another one that says 6% to 12%. So the interval for the difference is negative numbers, or the interval for the difference is positive numbers, right? And we're using it to estimate the difference between American, right, that's the Americans here, and the Scottish here. Now, If the interval contains nothing but negative numbers, doesn't that mean that we're pretty confident that this fella here, the difference, is negative? That makes sense? If these are negative, then that's negative. And if you do a little bit of math, add P2 to both sides. If you see a negative answer, doesn't that make P1 less than P2? So I can look at the difference between two groups and I can say that first group does whatever it is less times than the other group does, right? The proportion is less. If it is positive, however, right, so the difference is always one of these positive numbers, then it means it goes that way. And doesn't that now tell me that Americans would drink more than Scottish people? This would be Americans drink less than Scottish people. And sometimes, unfortunately, this happens. The interval of the difference between the two has negative numbers through to 0 all the way back up to positive numbers. In this situation here, do you know you cannot really say one group drinks more or less than the other group? Couldn't it be on this side, Americans drink less, but on this side, couldn't it be the Scottish people drink less? So we are going to look at this fella. So I need a confidence interval. What do you want? Anybody got a preference for what confidence interval we should get?
95.
We got it. But we're going to do it all in the calculator, right? So I'm not going to show you what the numerical calculation is. It involves a pretty messy calculation, to be honest. And there's a couple of different versions. So, and there's going to be a little kicker in the tail here. I'm going to go over to tests. Kind of where everything lives, isn't it? Over here. Now, we are looking for an interval. And I'll just scroll a little bit further. Do you see the guy called B? 2 proportion Z interval. Do you see that? It's very cryptic. 2 prop Z int. So just to remind you where it came from, you press stats, then you choose tests, and then you go to choice B, which is called 2 proportion Z interval. Right, so I'm going to choose that one. I'm going to hit enter. And we are asked various things. So let's see how they go. Oh, I didn't explain that, but I think it's obvious. Do you realize why I called these N1s and P1s and these N2s and Ps2s? Does that kind of make sense? So that you could tell which one was the first group and which one was the second. So X1 is going to be Americans, and the X represents those who said yes to I drink regularly. So that's that bit done. And then how many people? Well, the sample for the Americans was 1,000. And then we move over to the Scottish people, and there was 300 of those who said they drank out of 500. The interval that we've decided on is 0. I've lost it, 95. And now I'm going to hit calculate. And in this case, we got negative 3997 and then negative 0.2983. Oh, there's a point there. Let's make this negative 40%. And let's make this negative 30%. Would you agree that that is definitely nothing but negative numbers? And so won't our conclusion be that Americans drink less frequently than Scottish. Right. If the interval is negative, the first thing is less than the second. If the interval is positive, the first thing is going to be bigger than the second. So I can say that I am 95% confident that Americans drink less than Scottish people. Would you agree that that's pretty convincing evidence on really good sample sizes? I can even throw in a little bit more. Not only do I know that the Americans drink, percentage-wise, fewer of them than Scottish, but I can say I'm 90% confident that the Americans drink 30% less than the Scots. Even on a good day, is it the lowest answer, right? The lowest difference, isn't it 30%? So if the Americans came out of this, which I should be able to do that right now, the American number ended up being 25.1%, and the Scottish number, that's this guy here, ended up being 60%. And that kind of backs it up. Wouldn't you agree that this guy here is at least 30% less than that? Probably more, but at least 30. Now, comparing two proportions is quite a common thing to do. Sometimes you're doing it because you want to see if something has changed over time. So let's suppose that a social scientist, this is the kind of thing they might be interested in, that a social scientist looked back and found a paper that was talking about marriage, and it was asking 20-year-olds whether they were going to whether they were planning to get married in the next year, right? So they picked one age group, 20-year-olds, and they asked them, were they planning to get married in the next year? And A was from the 1950s. And he goes and, well, let's finish off this data. Right, in this data, there was 100 people, and 21 of them said that they intended or were planning to get married in the next year. Right, so what, 21%. And he is wondering whether social norms have changed, and he decided to do his own, paper on it. So he goes back and he gets some money, and he gets some money to conduct a little 200, people survey. And he comes out and he finds out of that 200 people, 35 of them said they intended to get married. So that's 20-year-olds from today compared to 20-year-olds from the 1950. And what he's interested in finding out is, have things really changed? Did people seem less likely to get married? Did they seem more likely to get married? Or maybe there's no evidence that there's been any change through that time period. Now, if I look at this guy here, if you just look at the raw data, would you agree that it looks like the percentage who intended to get married has gone down, right? But could it not just happen by the randomness of samples? That's why we're doing all this heavy-duty math stuff, right? So we're going to create, let's do a 90% confidence interval of the difference between them. And we'll see whether or not that difference is statistically significant, or whether it's just within the usual randomness. Do you know if I did another 200, wouldn't I get a different answer? If I did another 200 people, wouldn't I get a different answer? Every sample's a little bit different from the last one, right? And could you imagine if you could go back in time and do 2 or 3 of these, wouldn't these vary? Maybe the next time it was 20% and next time it's 22. So can you imagine both of these are varying a little bit? So couldn't it be that that's just randomness and there isn't much difference? Well, the only way to really do it is by conducting this little experiment where we are going to find, excuse me, that guy, B. And so there was 100, the 1950 20-year-olds, and 21 of them said they intended to get married or planned to. In the second group, there was 200 in that sample, and there was 35 of those. And we're going to do it on a 90% confidence interval. And here's
I think.
Oops, what did I do wrong?
I think you switched the X's and the N's.
Oh. Well, that error, that error kind of told me I probably screwed up, but I'll hopefully be able to fix it, right? Oh,
I've done that too.
it happens, right? I got yeah, it's kind of hard for 100 people out of 21 to say yes to anything. So I guess if I'd looked, I would have noticed that. So it's 21 out of 100, and then it is 35 people out of 200. And now we should get an answer. And the answer I got was negative 0.04 and positive 0.11. Oh. Basically, if I turn that into percentages, because my brain works better with percentages, isn't there no real evidence that these are different? I can't say, like in the other example, right, Scots people or Americans definitely drink less than Scottish people because the interval for the differences were negative numbers, right? Negative numbers, first guy less than second. Can you see here that it could be negative, right? But couldn't it also be positive? And could it also be 0, which means there was no difference at all? Now, what you might, well, let's kind of wind back a bit. This social scientist was hoping to see that this had changed, because change is important, right? It's important that you say, it's very few papers ever get written that said, in 1950, Americans did this, and 2020, they're still doing it. Because people are going to say, well, you've not really told me much, right? You tend to publish papers to say, something has changed. It's got bigger, it's got smaller, right? But something has changed. And in this case, you're stuck. So you might think, well, what does that social scientist do if he strongly believes that there is some differences here? He can't just pretend that that's not the numbers. Yeah, he can't cheat. He can't go and just stick in a negative there and call it good, right? He's not allowed to do that. What he could do is, couldn't he up this interval? Couldn't he ask 2,000 people? So he might go back to the government or his university or whoever's paying for it and says, I can't do it. 200's just too small, right? I can't prove anything. Give me some more people. And if he asks really nicely, maybe he'll get 2,000. Right? And just pretend, I know it's very unlikely. Do you see all I've done here is up the number, right? I've kept everything else the same, right? I've kept the percentage the same. This is 2,000 now, right? Instead of 200. I'm now going to redo this calculation, and this interval will change. Because typically, if you use more people, don't you get a more accurate answer? And won't more accurate answers tend to shrink? So what I'm hoping is that this interval shrinks enough that everything is negative. Let's find out if it is. Well, I can keep the 1950 data because I can't go back in time and say, could you do that with 2,000 people, please? Because I need better data. So I'm kind of stuck with the accuracy of this one, right? But I do have control over this one. Oh. It helped, but it didn't really help much. So do you know what I'm going to have to do? I'm just going to have to accept that if there is a difference, it's so negligible you can't find it. And that this was just caused by randomness. So I can't really say it hasn't changed. I just can't say for sure that I can prove that it has changed. That might seem like the same thing, but it isn't really, right? I can't prove that it's different, is all I can say. Now, that probably means, and I made these data up, right? My best guess is if I got real data on this, that would have changed. Would you agree that probably in the 1950s, thinking about getting married and being married was much higher on the scale of things people would do. And today, I don't know how many 20-year-olds are thinking of that kind of commitment of being married, right? So my guesstimate, if I got real data here, that would be significant, right? We'd be able to publish a paper and say, hey guys, you already know this, but hey, I've now proved it, right? And I might be able to put a number on it. So can we pretend a totally different story where I got real data and it was negative 5% to negative 4%, right? I got real good data. Wouldn't that mean there we go. Wouldn't that mean this is bigger than that? And I could probably say 4% bigger, right? 4% more people were thinking about getting married in 1950 than the 20-year-olds of today would be. Does that work? Right, just the statistical process. Sometimes you have to just give up. You may totally believe that something's true if you're a social scientist. I mean, your intuition and your gut feeling is doing it. But see if the data doesn't, right? If it just says you can't tell, you just have to accept it.
Is it,
yeah.
to me, it almost seems kind of cheating a bit to use two different sample sizes for two different samples. Is that?
I don't know about cheating. I think fairness would be a better way, right?
Yeah, it's not as fair.
It would be fairer to give both samples the same. Sometimes it's just coincidence or it's just circumstances. I can't go back to 1950. If they only had 150 people or 200, I got to use it. Sometimes it's to do with circumstances. Maybe it's easier to find Americans to ask, do you drink, than to find Scottish people, right? The good thing is that the statistics doesn't care. It might seem a little bit imbalanced, but the way it's calculated takes that into account. So I've got a strong suspicion that because this number is 100, isn't it going to be really hard to prove a difference? Because 100 is a very small sample size. And that's probably the drag. I might have to go to like 20,000 before I could get enough disparity between them to get evidence.
Okay.
And are we getting comfortable with this process? Because it's mostly calculator, right? And then you have a little interpretation at the end. I think I should try one more. Let's see if we can do a class thing. If we can't get a class thing, I'll do something else. Let's see what kind of numbers we've got. No, we can't. There's too many females. Right. It's not, I don't know, I'm stuck in, I should stop digging. for this question, I wanted like a jump, so many guys, so many girls, and then I could ask a question. So it's not going to happen. So we're going to have to invent something different. And I need two groups. So we're going to split you into the nursing people and the not nursing people, right? So if you're a nursing major, you're going to ask yes or no. You're going to ask yes or no to this question. And if you're not a nursing person. So let's see if that's actually going to give me any kind of data at all. So can you do a little hands up wavy thing if you're nursing people? I got 2 of you, 3, 4, 5. Okay, we can handle that. It's an atrociously bad sample size, but I'm living with it. Now, 2, 4, 5, 10, 15, 20. Okay. Now I have to ask a question of both groups, and we'll see if there's any major differences between you, right? Try to think something nursing people might answer yes to more than people who are not going into nursing. That's an interesting question. What could I ask? Well, nurses are very caring people, and caring people tend to have certain things that they gravitate towards. I'm trying to think of something that a caring person would like. Oh, here we go. May not work, and you may choose not to answer this one. How many of you have cried watching a movie? If you want to answer, I'm only asking the nursing people right now, right? So how many of the nursing folk have cried during, oh God.
Remove mine for Rachel.
Oh, okay. Can I just pretend I never saw one of you?
Oh.
Right? Okay, now the not nursing people, and there's 15 of you. How many of you have cried watching a movie? 1, 2, 3, 2, 4, 5, 2, 4, 5, 6. Okay. Anybody else? Okay, it's 6 out of 15. So here is our raw data. So I'm going to see whether or not there's evidence to show. Oh, was I already on this sheet, right? There's evidence to show that nursing people cry more at watching movies than people who are not in the nursing. So this is what, 80%, right? I'm just getting the number to compare them. Let's see what 6 divided by 15 is. Oops. Should be a nice number actually, but I can't do it in my head. 40%, wow. A ratio of 2 to 1. Superficially, doesn't that look like pretty strong evidence that nurses cry more at movies than non-nurses? But it is atrociously bad sample size. So we may not get the interval having nothing but positive numbers, because remember, positive numbers mean first guy bigger than second guy. Oh, I need a confidence interval. Let's pick 90. Okay, here goes. Stats, tests. And it's 4 out of 5 and 6 out of 15 at a 90% level. And the answer that we get is 0.04 to 0.76, and we have nailed it. Nurses cry more at movies than non-nurses. All positive, right? And when it's all positive, it means percentage of all nurses who cry at movies is bigger than the percentage of all non-nurses who cry at movies. And if I wanted to, couldn't I say at least 4% more of you cry than non-nurses? You see this number here. Do you notice how huge that interval is? Can you tell why it's so huge? Can you just look at the sample sizes? You see these guys up here? That's what caused it. The fact that I was actually able to get statistically significant evidence is actually very surprising. I think the reason it worked was, aren't these numbers so different from each other? 80% against 40%, that contributed to helping the interval go positive. It's quite interesting, isn't it? I think so. Couple of little tidy up things, and then I'm going to just call it good. So we're going to finish early today. I'll give you a chance to get on with your homework. I'll hang about for questions, of course. So what's left? I haven't talked about when you're allowed to do this. There are conditions. And you know you have those A, B, C, D questions where you have little dots and you pick. You're going to get questions like that. So let's take you through the conditions. Some of them you never get asked, but I'm going to put them in anyway. Isn't that basically true for everything that we've been doing? Not just this, but everything for the last 5 weeks. Your sample, shouldn't it be a simple random sample? Agreed? Again, they probably won't ask this, but I'm putting it anyway. Shouldn't I ask the question in an unbiased way? Simply, I should have said, have you ever cried at a movie? Right? Or something like that. I shouldn't try and influence that answer. I'm trying to think of a biased way of saying that. Yeah. Are you a big wussy and have you ever cried at a movie? Right? I mean, that's not a very good example, but you know what I'm doing. I'm trying to influence you. In that case, I'm trying to stop you from saying yes, right? Not a good way to ask any question, nor should you. The sample needs to be big. Now, what on earth does that mean? Well, remember it was when we were doing the means, wasn't it? It had to be, I think the textbook went for 30. Was that their kind of run of the mill? You need 30 people if sigma is unknown. And if you know sigma, you can get away with 2 people, but you shouldn't really. But theoretically, you can get away with anybody. But if it's sigma is known, you can pretty much have any sample size, and theoretically at least it would work. If sigma is unknown, I think the rule was bigger than 30, right? So what does big mean in this context? Well, you'll see it written down like this. And in English, when you do a proportion question, your sample, at least 5 people have to have said yes to the question. That's what that ends up being. And at least 5 people had to have said no. By the way, if you go back to my really interesting answer, the one I was happy about, do you know it failed under that test? I only had 5 people. Didn't 4 of you say yes and 1 of you said no? So it wouldn't have worked. But let's pretend I didn't tell you that, and so we can keep the answer for that one. This is bad, but you'll have to use it. Every textbook that I've ever seen, it should be 10. Right? Will we just put it down to one of the many idiosyncrasies that this textbook has? Like 80% confidence intervals and weird labeling of histograms. And I've forgotten, but doesn't it have another weird one that I complain about a lot? Just can't remember what it is now. Oh, 2.5 standard deviations away from the mean is an outlier. Really should be 3. At least everybody else says it should be 3. Remember that one? Actually, it was fine with you remember the interquartile range one? You know, the 1.5 thing? That was perfectly fine. Everybody agrees on that one. You just seem to have some differences. So you're going to have to just pretend, for the sake of this homework, that when you're asked what conditions have to be true and you're meant to pick, you know, maybe a couple of places, you're going to pick NP greater than 5, NQ greater than 5 is one of the reasons, one of the conditions that has to be true. Are we cool? Is there any questions? Right. Knowing me, I want one last thing. I am going to load up the homework and we're going to scan through it in case I miss somebody, because it has been known. Okay, should be ready to go. Oh, I have 2 choices there. I'm not sure which one it is. I think it's this one. Let me check. Are you looking at 7.4? I'm scrolling up and down. Are you seeing 7.4? Okay, we're good. Right. The first part is going to be about finding differences between means, and we kind of covered that yesterday. So I'm just going to cut to the chase. And here's our first one. Most married couples have 2 or 3 personality preferences in common. You didn't know that, did you? If you're married. Zoe, did you know that you have at least 2 or 3 with your partner?
Oh, for sure.
Okay. Since I'm nosy, let me pick some. Do both of you like a particular genre of movies? Like you both like westerns, or you both like comedies, or you both like sci-fi? That would count, I think, as one of those things. Do you share anything like that?
Not really. I like horror movies and he likes action movies.
Okay, so that one's not going to help. Do you both like traveling?
Yeah.
Okay, so that would count as one. Do you both like kids, even if you haven't got any of your own? Do you like kids?
We like other people's kids, yeah.
Well, that counts because you share the same view, right? You're not sure about yours, but you quite like other people's. So, okay, I got you. Can you think of a third one? I just want to see if this is real or not.
We both like STEM, science stuff.
Okay, right. So you're a classic example of what they're saying here, right? That most married couples have at least 3 things in common. Personality preferences, I guess they call it. Now, a random sample of 364 married couples found that 134 of them had 3 preferences in common, and another random sample of 582 showed that 218 had 2 personality preferences. So the groups here are people who are married that have 3 things in common, and the other group is people who are married that have 2 things in common. And can you see that's basically your N1 and your X1 and your N2 and your X2. And then you go and you create a 99% confidence interval. And in this case here, oh, I'm glad I kept the answers. Can you see that's -9% to +7%? Right? Now, what that is telling me is, isn't there no provable difference between the 2 groups? See, if that interval was full of nothing but positive numbers, wouldn't we be able to say the percentage who have 3 in common is higher than the percentage that only have 2 in common, right? The fact that it's got a negative and a positive in the interval, doesn't that mean, well, you can't tell, right? And examine the confidence interval and explain what it means. Now, because the interval contains positive and negative numbers, we cannot say that one of them is higher than the other, right? So that's that little tag on at the end kind of thing. We're quite comfortable about how these questions are going to have a story attached to them, but the story is going to have two groups, and each group's going to have a percentage attached, attached to it, and then off you go and you do a confidence interval. So here's another one to do with something to do in the Navajo reservation. I'm not getting into the details here, but here's the answer. It's somewhere between 5 and 20%. 5%, right, positive, 20% still positive. Does it not mean the first group has more of whatever it is than the second group? And I guess if I went back to the story, it might be the first group made more pottery than the second group, or the first group had more houses or more percentage of whatever it is. I guess I should read it and find out what it is. Oh, so it's what percentage of your houses were in the traditional style of that native population, right? So evidently, the first place had more traditional houses than the second. Interesting. Useless piece of information, but I like telling you useless. If you go to Ireland, they have a really cool thing that they don't do as much in Scotland. They do a little bit in Scotland, but they go overboard in Ireland. They have tons and tons of tiny little houses, right? That's kind of the size. And they're very often 150, 200, whatever, years old. And they paint them. And they don't just paint them like your colours. You can imagine a string of 10 houses. They are bright orange, green, yellow, pink. I mean, really out there colours. Not, mauve and kind of cream, right? Although I'm sure there's a couple of those. And it's really pretty. You just drive along and it adds a bit of colour, because Ireland's very green, right? Just like Scotland. Well, Highlands of Scotland are, but the valleys of Scotland are. So I think they put a lot of colour in it just to break up the greenness. Because can you imagine it was just green and grey, because the stone, they're all built in stone, right? Green and grey would be kind of boring. But what about green and pink? That's got a colour scheme out of the blue. So have a look at it. It's really pretty. That's one of the things my wife noticed as well. I think we're finished with this. Yeah. Oh, well, here's a long one, but you can do that yourself. They do a before and then they do a kind of after, and you're going to look to see if there's changes. And, I guess I should do 16 because it's not a real calculation, it's a theory kind of thing. Suppose a 95% confidence interval for the difference of means contains positive and negative numbers. Right, so you did a 95% confidence interval. Imagine it was from here to here, and it had positive and negative numbers in it. Will a 99% confidence interval, based on the same data, contain positive and negative numbers? Right, so there's 95, positive and negative numbers. If I move 95 to 99, don't you make the interval get bigger? Now, if this has got positive and negative numbers in it, if you make it bigger, don't you just get some more negatives and some more positives? Do you see, it's kind of guaranteed. So that's why it's the top one. Suppose you have your 95% confidence interval and it contains nothing but positive numbers, right? So it's kind of over here, oops, kind of over here, right? Nothing but positive numbers. If you move out to 99, couldn't you end up catching some negative numbers? So to finish with this, let me show you what that might look like in numbers. What I'm trying to get here is sometimes you have to be careful about the conclusion that someone makes. Let's suppose we did the Americans and the Scottish people, right, and how much they drank, right? Let's suppose we did it again, right? And we got the answer this time that, just to make my life easy, somewhere between 4% and 6%, right? But that was a 90% confidence interval. Now, if this was true, wouldn't Americans drink more than Scottish, right? Everybody's positive, first guy bigger than second, right? Now, if I moved this up to a 99% confidence interval, could you imagine it might end up being -1 to 8%? If I did a 99% confidence interval, I'll no longer be able to say, oh, I have proved that Americans drink more than Scottish, right? I've changed the story around. But can you see, I can't prove it anymore because negative and positive. It's the same data. Isn't the only difference the confidence interval? If you want to be 99% sure, doesn't that mean sometimes you have to give up some answers that you were happy about? Now, if you're unscrupulous, wouldn't you do a 90, a 95, and a 99 for the same set of data? And if one of those three gave you nothing but positives or nothing but negatives, wouldn't that be the one you publish? Because nobody's going to publish a paper saying, I'm a social scientist. I've just proved or found out that I can't tell if Scottish or Americans drink more than each other. Which is what that is saying, right? That never gets published, right? Nobody pays attention to, I can't tell, right? I can't tell lots of things. I guess if that was allowed, couldn't I make lots of money by just publishing papers? Probably at that Harvard University where that guy came from, since I'm a statistical expert. And I could publish lots of things like, I don't know what the percentage of people who have COVID is. I can't tell. I don't know what percentage of them die. I can't tell. Right? Stupid, right? If you were really, really, really unscrupulous, wouldn't you do 2 samples and it didn't work? Wouldn't you do 2 more samples and it didn't work? Wouldn't you just keep going until you got 2 samples that did work and only publish that one? Can you see how you can cheat? So how do you know? Pay attention to the people who are telling you. If the, well, I don't know. If the American Coffee Society publishes a paper that says coffee is good for you by this % compared to people who drink milk or whatever the other group is, because it's the Coffee Society of America, shouldn't you be a little bit dubious about anything to do with coffee? And if it's the Republican Party who's done a poll on something to do with what we think about taxes, or if it's the Republican Party and what we think about taxes, should you be really, really skeptical about whether you should accept their results, right? So look at who paid the money is one way of avoiding that. Or, with the exception of Harvard, who's now off my list, if it's a prestigious university or apolitical organization that have no axe to grind, believe them, right? If they give you some information, believe them, right? But just at least be skeptical of the other people. I think I'm not saying that they're lying. They may well have done a really good survey and it's true data, but at least be skeptical of it, because I think that's safe. I have one motto to do with politicians: they are lying unless proved otherwise. That's a very good way of looking at them. That guy's lying to me unless later on I've got other evidence to prove he was telling the truth. But that is me. We're going to finish early. I think it's a good place to finish at the end of something rather than start something and then have to basically restart it again on Monday. So any questions, hang about. And don't. I haven't taken this class set yet. Sorry about that. Give me a few seconds. You want to smile this time? Okay, we got you. I missed it. Sorry, you can smile again. Where is it? I can't press it. I'm having technical issues. Hold on a second. I'm desperately hitting this button. Got it. Wow. You know your face is going to hurt if you smell that long. Okay, you are captured and you are good. Right. So as I say, I'm going to hang about. If you have any questions, if there's something that you want to talk about, we can do that. And see you Monday.
Thank you. Have a good weekend.
Thank you.
Scare you. 1 week, 1 day. 5 more classes and a final. Are you suitably scared? 5 classes and a final.
2 things I wanted to say.
Yes.
One is in the beginning when we were looking at that, COVID, the Harvard scientists
Thing, right?
Could it also be that whoever put that on there, it's not necessarily the Harvard people who are doing it, but somebody else who twisted that information, got the information from Harvard, and then said,
yeah. Yes. And that wouldn't surprise me.
that they
I guess I have been cruel to that guy. But if I was that guy, I would be. I don't know if you can sue newspapers for that, because technically that might have been one of the. He doesn't just give one thing. Imagine he might have given a density one, which is the one I would have used, and then he gave a raw data one. And the guy who's doing the article liked the raw data one because it kind of was what he wanted to be true, right? And he didn't like the density one because it wasn't really what he wanted, right? I could see that happening. I don't know if the guy could sue it, but I think he would be really unhappy that people could take good science and cherry pick the bits that look a certain way. The best way to check that, I don't know where that article came from, although it was in MSN, so I know they're quite liberal. So you may want to look at, if you find that chart again, find out who did the article, and if it's a left-leaning organization, then it might have been politically biased. If it's an organization that's got nothing to do with politics, it's just a guy who doesn't know statistics. And I guess he just picked it because it looked pretty. And he decided that it was evidence that you should close 13 states.
Okay, and then the other question I had was right at the very end of what you were talking about. You were saying if you want 99% confidence, you might lose some, and then I didn't get.
Oh, you might lose the ability to say that you have proved that the first group is bigger than the second. So, if you do it in 90, everybody's positive. So you can say Americans drink more than Scottish, if that was the story. That's on a 90% confidence interval. But if you increase it to a 99% confidence interval, your interval may not have positive numbers anymore. It may have negative and positive. And the minute that happens, you cannot say the first group is now bigger than the second. And in many situations, that's kind of what you want. Don't you want one group to be bigger or less than the second? Because what that's showing is that there's a statistical difference between them, right? There's a provable difference. It's not very helpful to say you can't tell. You really haven't got much when you do that. Another way you can detect that, if you read the small print, if there's a whole load of different percentage comparison things going on, like it's a big report, if you notice that they switch the confidence intervals, like sometimes it's 90 and sometimes it's 95, and then now and again it's 99. So can you imagine they did comparisons of lots and lots of different pairings, like 20 different comparisons, and every single one of them, the first guy was bigger than the second. See, I've got evidence, whatever it is happening. If you notice that in some of them it was a 90% confidence, and then in some it was a 95, and it was someone as a 99, that makes me very suspicious that they were cherry picking the confidence interval to use to make sure that it was always positives or always negatives. Because if you're really doing something like that, shouldn't you commit yourself 95 all the time, 99 all the time?